Let's talk about R square and adjusted R square in this video. So we have all learned the first algorithm which we have explored was a linear regression. After understanding the concepts of linear regression and how the algorithm works, I'm really excited to use it and make predictions on a problem statement. I'm sure most of you would have done the same, but once we have predicted the values, what is next? Then comes the tricky part, right? Choosing the most appropriate evaluation metric is a crucial task. R-square and adjusted R-square are such two evaluation metrics that might seem confusing initially, but they both are extremely important to evaluate regression problems. Now, let us try to understand. Um, to understand these concepts clearly, we are going to take up a simple regression problem here. Okay, here we are trying to predict the values of x and y. I just wanted to take one regression problem. Let me take an x-axis and y-axis, put all the data points like I have done in our earlier videos. So I want to simply draw a line from here which is passing through 0. Let me say that this is our regression line, right? Here what I'm trying to do here is I'm just trying to predict the values of y based on the values of x, right? So this is how we can plot a simply a regression line, right? Now these green points represent the data points, and the the black line here is our predicted regression line. So this is our predicted regression line, and these green points will be our data points. Now so how do we evaluate the predictions from a regression line using the data? Well, we could start by determining the residual values for the data points. What is a residual value here? Residual, I can write, residual can be equal to, residual is equal to predicted, actual minus predicted, and actual will be denoted as y and the predicted will be denoted as y hat. Okay, what I'm trying to do here is uh, I wanted to you know uh, I wanted to find the difference between actual. Your green point is an actual and this black line is a predicted value. So I just wanted to put the difference quite minimum. Now what I would like to do here is I wanted to write an equation for residual sum of squares, which is also called as RSS, which is equal to summation of yi minus yi hat. Here yi will be the data point, this is yi, and yi hat will be the point on the regression line. Okay, so this is what we have understood for from residual sum of squares. So we also have another one which is called total sum of square. Total, let me take red point. Total sum of square, which is also given as an equation called yi minus yi mean. This time here it is yi mean. What is this value here? We are trying to draw a line here. We are trying to draw a line here. This point will be your mean, which is represented as like this, and the rest of the points will be the data set. Here those are the points. Now what we are trying to find is we are trying to find the value from the data set to the value of mean. So that is called as total sum of squares. Here, if we wanted to write the formula for r square, I can write here r square is equal to just wanted to use a green color. R square is equal to 1 minus residual sum of square divided by total sum of square, right? This I can also write it as 1 minus summation of yi minus yi hat whole square divided by summation of yi minus y mean whole square. Now from this equation, uh, can we can observe few things here. So suppose if you want, if you are predicting this line, you know, this is our prediction line, right? This black line is a prediction line, and this prediction line and the data points are minimal. If that is a very close, then this value will be quite low, right? And when this value is low, and if this value is high, if this value is high, what we will get here is a big number, right? What we'll get here is big number, because 1 minus of a small number will become a big number. So when a big number, when a small number divides by big number, will be giving obviously a small number, right? As a whole, when you subtract with 1, then you will get a big number. The big number means the accuracy will be good. It will be a good accuracy, right? Now what we are trying to do here is, okay, but there is a problem here. Suppose if I have some multiple features here, let me just say that bedroom will be my independent feature, and I have another one which is called as location, which is also an independent feature. And let's say there is a price. Depending on these two, I mean, depending on these independent variables, the price will be decided. So this is our output variable, and these both are our input variables, input 1 and input 2, let us say. So this is what the data set we have actually. Now while while doing uh, uh, while doing the performance matrix for this data, suppose we have got r square is equal to some 90%, right? 90%. Now if you're adding another feature which is called gender, in this, gender will be nowhere correlated with price, because there is no correlation between gender and price. But even though when you're using this model, then your r square will be getting increased to 91%, which it should not actually supposed to do. But in general, it is going to happen when you are increasing the features, right? So this is a problem with r square. That's why we have adjusted r square. There comes adjusted r square. This problem can be rectified with adjusted r square. So in adjusted r square, the formula will be given as 1 minus r square into n minus 1 divides by n minus p minus 1. Suppose we have a problem, we have the same problem like this. Okay, now we have the same problem. Now by using these two features, let us say that here n is the number of data points, and p is the number of predictions, right? Now what I would like to do here is, I wanted to use this table. Okay, let us say that we have um, this table I wanted to use, and these are all independent variables, and this is a dependent variable, and these are all independent variables. Now initially let us use bedroom and location as the input features and price as an output feature. So let us say p is equal to 2 initially. P means number of predictors, number of features. Okay, here when p is equal to 2, we have got r square is equal to 90%, right? Now we have also have adjusted r square, which we have got some 86%. Now we wanted to add additional feature which is called gender in this case. So this time what we will have, p is equal to 3 here in this case. Now what r square will have, let us say r square, I mean this time we have increased the features, so r square will take 1% extra, which is 91%, which it is not supposed to be, but it is going to happen here in r square performance in r square performance. So here in this case, adjusted r square will be adjusted r square will be 82%, which is actually expected, like which is actually to be true. So this problem we can solve by using adjusted r square, by using this equation. This equation will be in such a way that whenever you are adding additional features, your adjusted r square will be decreasing further. All right. So if you increase more and more features, the adjusted r square will be decreasing, and here r square will be actually increasing. So this problem we can avoid by using adjusted r square. All right, this is it in this video. We'll see you in the next one. Thank you.